Welcome. Again, my name is Jason Green. I'm with Corning. I run our technical resource team for the One Platform. We call it the Solution Architecture Group. And so what we do is we design and consult with customers about their network. So what we're going to be talking about today, the title of this session is The Future of In-Building Networks. And the two really areas that we see as coming up and coming, or the newest thing to hit the in-building field, is software-defined networking, or SDN. And then where we believe it's going in terms of enabling the full capabilities of SDN is a high bandwidth, low latency network, which is the deep fiber platform that we tend to design into systems. So as we talk about SDN, what SDN is doing is we're essentially separating out the intelligence from the hardware. So on a traditional network, we have switches and routers, and those switches and routers, they have all of the intelligence built into the hardware itself. And so what we do with SDN is now we're separating the intelligence out of that. So now we have what I'll call, dumbish boxes, but we have a more intelligent overall system, because now we have this control plane, or this orchestration platform, which is essentially be able to control all of my switches and my routers in a given network. And so as we talk about separating this intelligence away from the hardware, this is not something that's new for us in IT, those of us that have been here for a while. So the first time we did this is back in the late 90s. We talked about SANs, or storage area networks. And in storage area networks, if you remember, before storage area networks, when we talked about storing data, we had a file server, and that file server had hard drives, it had access control list, it had an OS, and if anything happened to that box, if a power supply died, if my hard drive got corrupted or damaged, my data was gone. So what we did in 1999 with SANs, I was doing this in my previous life. What we would do is we separated this out. So now I had a control mechanism, or I had essentially the brains of the system, and now I had multiple file servers that had this data on it. And with this control mechanism, now I can essentially tell my data where it goes. So now if I have one storage device that fails, I still have my data, right? So I can essentially, it's backed up, and I can go to different file servers. We have also done this with computers. So if you think of computers, in a traditional computer, when we think about computers, we have essentially an OS that's installed on a box or on hardware. And on that hardware, we have hard drives, we have our OS, we have all of the various applications that we want to run on that computer, right? If we go back a while, right? But now, nowadays we have what we call virtualization, or VMware, where the vast majority of enterprises, I think up to over 80% today, they use virtualization. So now instead of having my computer with all my intelligence on that hard drive, if I have a power supply that fails, or if I get that blue screen that we don't like seeing, all my data is safe, right? Because it's actually going up to, it's got some north-south traffic, and all that's getting saved, right? So with virtualization, what we did, again, is we pulled out that intelligence. So now if I have a Windows 12 operating system as an example, I can have multiple OS sessions going on in the cloud, which is hitting multiple computers, or really workstations at this point. So when I say a workstation, I mean if you're a bank teller, you probably don't have a physical computer at your station. You have an x86 box, an Intel x86 box on the back of your monitor, which is connected to a keyboard and mouse, and all of your sessions are going north-south into this virtualization kind of computing platform. And so next on the horizon, and this has really happened in a big way since about 2013, is this software-defined networks. So the software-defined networks, we're doing the same things that we've done already with storage and we've done with computers, and that we're separating the intelligence again away from these boxes. So now I've got, I don't have to configure every single router and every single switch if I want to do a change. Now I have this intelligence that gets pulled out, which we call the control plane, or an orchestration platform. Now I can control all of my network from one location. So I've got this head of the octopus, and from this head of the octopus, now I can control in a very nuanced way my entire network. So if I want to make a change to my network, I don't have to dive into each router. I can do that from one place, and I can push it out to all of my workstations. So what we're going to do, we're going to dive into this a little bit deeper. We're going to shift to the whiteboard, and we're going to talk a little bit more about history, and I'm going to kind of tie that into a little bit more about how these buildings are changing in terms of a technology platform. So with that, we'll go to the whiteboard. All right, tying back into our history lesson. So if we go back to 1999, what was important to us in IT around 1999? What we were essentially doing is we were transferring files, right? So So when we go back, we think about FTP. So we were transferring videos, we were transferring picture files, we were emails, etc. So when we talk about 1999 and what was important to us, it was really the size of the pipe, right, or bandwidth. So what is bandwidth? Bandwidth is the width of the communications band. So we talk about bandwidth. And why was bandwidth important? Because we had big files and we were transferring them back and forth. So that's when we start talking about what is the size of your pipe. Is it a 5 megabit pipe? Is it a 1 megabit pipe? Is it a T1 service, etc. So in 1999, that's what was important to us, bandwidth or the size of the pipe. But then if we go forward a couple years, 2005-ish, we had a lot of things that happened to us which kind of changed our IT world a little bit. So when we talk about the services that came out in 2005, that's when we had Skype came out. Around then we had YouTube. VoIP phones started to become, coming out into the market. And so when we started to talk about Skype, YouTube, or VoIP, we talk about RTC or real-time communications. And so now it's not just transferring files back and forth like we did in 1999. Now what's important is actually the packets, right? So where in 1999 we were transferring big files across the pipe, going back and forth, now we're actually concerned about the individual packets and how they flow across that pipe, right? So when we talk about pipes, what's important in 2005 for Skype, YouTube, and VoIP is latency. And so if we call bandwidth the width of our pipe, latency, we can think about latency as the length of our pipe, okay? And so for Skype, YouTube, VoIP, when we got in 2005, now latency is important. So nice thing about what we're talking about here, software-defined networks and deep fiber architectures, bandwidth and latency really play into fiber very well. So when you talk about latency and bandwidth, we're measuring this in megabits, right? So a 5 megabit pipe, a 10 megabit pipe. We talk about latency, we're talking about time. So maybe this is a 20 millisecond pipe, right? And so when you talk about media, you don't get better than fiber, the speed of light in terms of latency. So that's what we were doing in 1999 and 2005. So with latency, what happened here is now we start concerning ourselves with quality of service. So with quality of service, again, we talk about the packet. So it's not only the size of the pipe, but we want to prioritize our pipe. So when we talk about quality of service, we're saying, okay, my SIP traffic or my VoIP traffic is a higher priority than my file transfer, my FTP kind of traffic. And so we want to prioritize in this way because what this allows us to do is this allows us to avoid jitter. So in the early days of VoIP, we had jitter, right? Same thing with YouTube and Skype. So we don't want to have, if those packets come across in the wrong order, we don't have a good experience. So that's 1999 and 2005. So next I'm going to flip my board here to get a little bit more room. And when we look to 2011, 2012, 2013, what happens is, essentially our network starts to get more complicated. So now we start talking about 2011, 2012, 2013 kind of time plane, and now we have many more devices on the network, and now it's difficult with quality of service. It's hard to say that SIP traffic, when we talk about quality of service again, before I drew out, we were saying, okay, well, SIP traffic is more important than FTP traffic. But when we get to 2011, 2012, 2013 with all the devices on the network, sometimes it might be that SIP is not my most important thing. And so I want to be able to basically use the full pipe that I have. So when we talk about bandwidth, when we're talking about prioritizing these patterns, basically what happens is I say part of that bandwidth pipe is dedicated for this, part of that bandwidth pipe is dedicated for this. This might be a higher priority, but what it doesn't allow me to do, it doesn't allow me to necessarily use my full pipe. So when we talk about VoIP traffic, sometimes maybe I'm using 70% of my pipe, but sometimes I might be using 5% or 0% of my pipe. So what software-defined networking is going to allow us to do, it's going to allow us to start to shape that traffic. And so if we tie this back to software-defined networking, we typically talk about two planes. We talk about the data plane. And so when I say data plane, think of data plane as your physical routers and your physical switches in a network, right? And so what are the routers and switches doing in your network? They're moving the the data from point A to point B, okay? And so these are my switches in a traditional network, all the intelligence, right? We talk about pulling the intelligence away from the hardware and software-defined networking. In a traditional network, the intelligence is built into those routers and built into those switches. So we have, in SDN, we separate the control plane from the data plane. So now I got the control plane. So you could think of the control plane as being essentially the intelligence or the brains of the network, right? So what the control planes does is that now it communicates, to all of my routers and all of my switches at the same time. So what that allows me to do in a very nuanced way, now I can shape my traffic. So if, let's say my CEO calls and says, hey, I've got an important conversation coming up with a client, and I want you to jump on a video chat with me. Well, to use that video chat, maybe I need to download an application onto my device, on my tablet. So now at this given time, SIP is not the most important thing to me. The most important priority for me at this given time is downloading that app. And so what SDN allows me to do, in real time, it allows me to kind of shape my traffic. And now I'm able to use my full pipe. So no longer can I say, well, I can't tap into that pipe because I've already got this much bandwidth associated with my VoIP phone, even if I'm not using that VoIP zone. I can shape it in real time. So that's what SDN is doing. So with that, I think we're going to pause again, and we'll start looking at the actual equipment in the lab here. Okay, so now you're thinking, Jason, this sounds great. Now I can shape my traffic, but what is a reason that I'd want to shape my traffic, right? So right now, I have my big sys switches, my big routers. Understand that with quality of service, I have to set my priorities. Well, what's a real-world scenario where I want to change the way my traffic flows? So the first example that I'll give you is day traders. So if you think about day traders, what they're doing is, we talked about bandwidth and latency. So for a day trader, bandwidth is not so important to them, right? Because again, they're not sending massive files back and forth, but latency is super important to them, right? So if I'm a day trader, holding on to a stock for 10 minutes might be a long time, right? So when I click that button to buy a stock or to sell a stock, I want it to be instantaneous. So we talk about milliseconds. Right, so now we want to have that. We want to have a fiber environment. We want that to be very fast, right? Because when that day trader hits the button, he wants to have a very low latency system. It wants to be instantaneous. But if I'm a day trader house, I might be willing to pay a big premium for that low latency service, right? I'm making a lot of money. No big deal if I have to pay a lot of money for that service, but I don't want to have to pay for it after hours, right? So maybe I can have some kind of setup where between 9 and 5 when I'm trading, or maybe I only trade in the morning. I can actually shape my traffic pattern where I say the priority for me, during trading hours is that button click, right? I want that button click to be instantaneous. But after that, maybe my SIP traffic is more important. Maybe I've got some FTP traffic that's more important. It's not the most critical thing. So again, I can shape my traffic depending on what I want to do. Another example that I think about is a call center. So in a call center, if we think about a call center today, I'm sure most people have seen a call center. You have a lot of employees sitting in a room and they're answering the phone. So in that case, on a call center, it's pretty intuitive to think from a quality of service standpoint, the most important thing is my VoIP traffic, right? If they're using VoIP phones, or maybe they're using a soft phone on their computer. So that particular application is the most critical thing for a call center. But we're in IT, right? So we got to think about years ahead, and maybe it's not even that many years ahead, where maybe it's not good enough for me to talk to somebody in my call center. Maybe I want to video chat with them, right? So maybe for very important customers, I want to video chat. So you can imagine where I might want to shape my traffic depending on who makes that phone call. If the phone call comes in as a voice phone call, then I want that to be the highest priority. If it comes in as a video chat, maybe that's a more important customer, or for whatever reason, I want that to be my highest priority. So that's another example of where I want to shape that traffic, which with SDN, which allow me to do in these kind of deep fiber architectures. The last example that I'm going to give is telesurgery, right? So when you think about telesurgery, right? So now I'm doing surgery and the doctor is not in the room, right? So again, we got to think about a couple years out. So, so now maybe I'm using a robot, maybe I'm using an assistant that's going to help me, but the guy that's actually calling the shots is not in the room with me, right? And so in a hospital, at any given time, I might want to shape that traffic in different ways, but when I'm doing an important surgery and my doctor is off-site, you better believe that that's going to be my #1 priority. So again, just another example of how we're able to shape the traffic, and we're able to do that in real time, or real-time communications, RTC. Okay, so now we've talked about a couple of examples, so now what we're going to do is we're going to start looking at the actual equipment that we deploy on site. And so what I'm going to do is I'm going to set the stage. I'm going to draw out some of the network topologies that we typically will design in my group, and then what we'll do is we'll take you to some of the actual kind of scenarios that we have in the lab, so you can see this kind of actually in a working environment. Okay, so before we start looking at the real equipment, sometimes it's helpful to kind of schematic out what we're going to see. So the first thing you're going to see is what we call the top of rack switch, or TOR. So this is going to be performing my, my routing function, again a software-defined router. So when you see this, what you're going to notice is it's a 1RU 48-port switch. So what we have on the switch is we have many SFP ports, or small form pluggable. So small form pluggable is just a standard, so I can plug in a RJ45 connection, I can plug in a single mode fiber connection, a multi-mode fiber connection, whatever is the most convenient for my application. So the purpose in life of this top of rack switch is this is going to be my connection point to all my applications. So in the lab what you'll see is I have some copper connections. These copper connections are going to some local controllers. So as an example, we have a controller for Wi-Fi. So whether it's a Ruckus Wi-Fi or Aruba or Cisco, I have a local controller in this case. We also have our COM2000 IPTV solution. So that's got a copper connection as well. So it's going to come in and connect to my top of rack switch via copper SFP. And then the various other applications. We have a call manager for my VoIP traffic as well, which has a local connection. Also with the SDN, we have virtual apps. So we have the ability to virtualize some of these apps. So as an example, instead of having a hard, in the rack Wi-Fi controller, I might have an option where I have something that's in the cloud. So maybe I have some other kind of app that's in the cloud here, right? And it's just getting a LAN connection into my top of rack switch. So again, everything's software defined and makes it very flexible. The next box that you'll see on the rack is what we call, in our terminology, an aggregation switch, or AGR. So when you look at the switch in the rack, it'll become obvious that it's physically the exact same switch. So again, it's another 48-port switch, okay? Where the purpose of the top of the rack switch is my connection to my various applications. So this is my routing. The aggregation switch is my distribution point. And so what I'm going to do is I'm going to connect this aggregation switch to my top of rack switch. I'll use a single mode fiber here. So typically, when convenient, we'll use a copper connection to some of these local controllers just because that's the connection point. Typically what we'll try to do when we leave that top of rack switch, we're going to want to use as much single mode fiber as we can, again, for this high bandwidth, low latency. That's kind of our universal media that works for all connections. So let's say I've got a single mode SFP, which is going to connect to my aggregation switch. So now my aggregation switch is connected via SFP. And I can connect multiple aggregation switches, however large my system is. So in the lab here, we have an aggregation switch which is in the same rack as a top of rack switch. This would be common for, we do this a lot in hospitality for mid-tier hotels, so 100-room hotels, 150-room hotels, where typically they're 3 or 4 stories. Makes sense to serve everything from one closet. That allows us to minimize IDF closets, potentially get another hotel room out of the mix. But in some cases, if it's a resort property, as an example, I want to use that single mode fiber. Again, I'm not distance limited because I'm fiber. Maybe I want to connect that aggregation switch in a different IDF closet or even in a different building. If it's a resort, maybe it's multiple buildings. So that's what we're doing with the aggregation switch. Again, I've got that connection into the top of rack, so now I have access to all of my applications, and now I'm going to distribute that out. So when I distribute it out, I'm going to use, the first example I'll use is active Ethernet. So for active Ethernet, I'm going to use in this example, a bi-directional SFP, so a single fiber, small form pluggable SFP. And then I'm going to have a fiber connection again, which is going to go all the way out to my in location. And at my in location, I will have an optical network terminal, ONT, or you can think about that as just a switch. So this is a point-to-point connection. In the case of the lab, all of these connections are gigabit. Right? So I have a full gigabit that's going over to my ONT. At that ONT, in that hotel example that I gave, maybe I've got a port which is a LAN connection going to a computer. I have a connection that's going to a Wi-Fi access point, and maybe there's a connection to a VoIP phone, as an example. Okay? But in some applications, when we start about technology, again, the SDN platform, we're talking about SDN here, is very flexible, so we support multiple technologies. So active Ethernet being one option. Another option would be passive optical LAN or POL or PON, passive optical networks. So in that case, again, we're just going to utilize SFP ports. So in the case of PON, I'm going to have an OLT SFP. And again, it's single mode fiber out, so single mode fiber throughout. I'm going to go down, and now instead of being point to point, it's going to be point to multi-point. Okay, so point to multi-point. Okay, so one fiber leaving, and this fiber hits an optical splitter. What an optical splitter is get a single fiber in and multiple fibers out. In this case, I'm going to use an example as a 1x32 splitter, a common splitter that we would use indoors, but we have many varieties. And so now, let's say the application is, maybe in this application, maybe it's a hospital, and there's a Bluetooth location. So Bluetooth location tends to be, low bandwidth, so I don't need a full gigabit pipe to feed each of those ONTs. So now I'm going to have many ONTs that get connected via that same fiber port out of my head-end equipment. And so now this ONT is going to feed some locators as an example, right? And from there I can feed many ONTs, right? So the key of this is the flexibility that both the software-defined network provides, right? So again, I can, now with a software-defined network, as we talked about earlier, I'm able to tune my traffic depending on the real time. So, and then I also, from a technology standpoint, I can bring a big pipe and not share at all, or I can bring a pipe and I can share just depending on what I want to do. The beauty with the software-defined network, again, is now in real time I can kind of use the full size of my pipe, right? If location is more important at one given time, I can prioritize that versus other applications. So with that, what we're going to do is we're going to stop over and stop looking at the stick diagrams and look at the real equipment. All right, so now this is the equipment that I drew on the whiteboard. Now we're going to see it in real life. So what you see here at the top of the rack, this is the top of the rack switch that I referenced. So this is performing my routing function. So I've got it's software defined. So the software function is the routing function is all via software. And so what you'll see is I have some SFP slots, right? SFP is small form pluggable, as we mentioned, and I've got some copper connections. So I've got copper connections. Each of these are going to a physical controller that's in the lab, right? So I have some local controllers in the lab, and then I also have some virtual apps. So virtual apps, now those are going off into the cloud, and I just have a LAN connection, essentially giving me that application to my network. All right, so this is my top of rack switch with my routing. Next below here, you'll see this is my aggregation switch. So quickly you'll see physically these two switches are exactly the same, just performing different functions via software. So I have a fiber connection which is connecting my top of rack switch, which is my brains, which is my connection to all my applications, all my services. That's connecting down to my aggregation switch. The aggregation switch is now my distribution point, so I'm distributing all the services to my various ONTs or switches throughout the lab. So here what you'll see is I have bi-die optics. So here's the SFP, so just a single fiber out, and this is my gigabit SFP, which is ultimately serving gigabit ONTs that are throughout the lab that we'll show you here in a second. What I'm also showing in the rack is a OLT, so this is a rack-based OLT. So this OLT is where my active Ethernet is point to point. My PON is point to multi-point, and so this is an OLT. I have my SFP OLT port here, right? So this fiber is going to ultimately hit an optical splitter and serve multiple ONTs in the system. The router for this OLT is still the same top of rack switch. So I'm performing the routing function for this OLT as well. At the very bottom of your rack, you'll see this is my, in the lab we also have our cellular DAS throughout. And so again, this is part of the converged system as well. If you look at the left-hand side of this box, we call this an integrated head-in unit. The left-hand side is my connection into my services. In the case of DAS, my services are AT&T, Verizon, T-Mobile, Sprint, etc. So this is my connection into their radios. On the right-hand side, this is acting very similar to the aggregation switch. This is my distribution. So I have fiber out of this box, which is ultimately serving my remote antenna units, which is providing my cellular coverage throughout the lab. So now I'm going to go to the right-hand side of the rack. This is where we're doing all our distribution. So I've got fiber, again, out of my cellular system. I've got fiber out of my PON. I've got fiber out of my aggregation switch. That's all going to go to my patch panel here on the right side of the rack. And so for my point-to-point connections, I simply have a jumper, which is going to the patch, which is going to go out the back, which is going to hit various areas of my lab. We have different verticals that we're showing. So my point-to-point connections is simply just a patch. I have my point-to-point, point-to-multipoint via the PON. So in that case, I have the PON optic is leaving, which is hitting the optical splitter. So when we drew that on the board, the optical splitter, I drew that as a triangle. One fiber in, multiple fibers out. What that looks like in real life is a panel. And so I've got a single fiber feeding the optical splitter, and then that gets split out to, in this case, up to 32 ONTs. And I have, in this case, 3 ONTs that are running here in the lab. Then on the far right-hand side of the panel, this is my copper distribution for the power. So in the lab, all of my devices are remotely powered. And so we have 2 ways that we're powering the various systems, two products we offer. One is the power supply unit, or the PSU. So the power supply unit has a bunch of 100-watt circuits. And so these black connections, you'll see I've got a black connection that leaves, that patches up here, and that's leaving via composite cable. So out the back of this box, I have my fiber connectivity, and I have my power. So I have copper and fiber under the same sheath, which is feeding composite cable to power my ONTs and my remote antenna units for cellular. But then I also have digital electricity. So we have in the lab, we have a public venue setup, which would be, in this case, we're simulating like a football stadium. So we have a lot of power needed at a single location. In that case, I'll use my digital electricity product. So with digital electricity, I can bring up to 1,000 watts of power to a receiver on the other side. And that receiver can actually accept 2,000 watts of power. So I can have 2 pairs feed a receiver for up to 2,000 watts, or I can just bring a single pair and I get 1,000 watts to that location and still stay within my electrical code because this is digital electricity. So we're actually pulsing that electricity and bringing it back down to analog electricity when we get back to the box. So with that, we'll pause again and we'll start looking at the individual verticals in the lab. Okay, so now we're at our end devices. So this is our example for a hotel room. Could be a patient room in a hospital, a dorm room if it's public education. And so if I open the curtain here, you'll see kind of the smarts of the system that are behind. So what I have is a composite cable that's feeding this. Again, that's getting fed, in this case, by the power supply unit, or the PSU. So a 1 fiber 2 conductor cable is feeding this wall plate. Okay, and now out the front I have a fiber connection, which is providing my high bandwidth, low latency connection, and I have my copper connection, which is just physically powering that ONT. So this fiber jumper and this copper is going into my optical network terminal. This is getting fed by that aggregation switch we talked about. So we've got a gigabit SFP that's feeding this ONT. Out of the ONT, I have, in this case, 4 PoE ports, power over Ethernet, and I'm connecting to various devices that would be in my hotel room, again, or my patient room or dorm room. So I've got one connection that's coming over here to my set-top box. My set-top box is driving my IPTV. I've got one category cable that's coming out, feeding my wireless access point. So this is the wireless access point for the room. And then I have another connection which is going here to the left, which is going to a VoIP phone. Okay, so it's just some applications that are all running via the lab. And so quickly, I can do a quick demonstration of what we're doing here. So here's my hotel. So one thing that hotelers are looking for now is, now we carry our content with us, right? No longer do we want to walk into a room and flip through the channels. You know, we want to use our Netflix. Again, north to south traffic. I want to connect to that Netflix server or Hulu or YouTube or whatever that happens to be. So what I can do is I can take my phone and I can say, okay, I'm going to Chromecast, and I just hit my Chromecast button here. And you'll see that I'll start Chromecasting my content, right? So again, so now my device, you know, is what's coming with me. I got the north to south traffic flow. What's important there is low latency, right? I don't want to have any jitter on this screen. So I want to have a high bandwidth, low latency connection. And this is kind of the setup that we would do in hospitality. So this is an example of a project where we would deploy a software-defined network, fiber-rich architecture. And in this case, we're supporting IPTV, Wi-Fi, and VoIP, or voice over IP. All right, so now we're going to walk over to the other side of the lab, and I'll show you another example of a deployment architecture. Okay, so here's some other deployment options that we're showing off in the lab. So this is actually another mock-up that we did for a customer. This happens to be a hotel as well, but you can imagine this could be a enterprise office building. But what you'll see is this is a media enclosure, and inside the media enclosure, in this case, I have a 4-fiber, 4-conductor composite cable feeding this box. And so what they've done is in each room in this case, they have this media enclosure with 4-fiber, 4 conductors. And what this allows us to do is this allows us to scale, and because I've got this fiber connection, we don't necessarily have to think about what we need today. We can think about what we need 5 years from today. So what we have out of the gate is I have a single ONT. That ONT gives me 4 power over Ethernet ports. So in a hotel case, that could be going to a TV, it could be going to a Wi-Fi access point, it could be going to a VoIP phone as an example. We have a VoIP phone set up here in this example. Also, in some of these hotels are also using plain old telephone service or just standard SIP traffic. So we also have a standard telephone right here that we're also showing in this case. But again, so you have your ONT, you have your punch downs. In this case, I wanted to see punch downs that are allowing for my IP connections and my telephone connections. But what we also can do here is you'll see this is where my fiber's coming in. I've got my copper splice there, which is just for the connectivity to powering that ONT. But you'll see I've got 4 conductors. So I've got up to, in this case, 200 watts of power that's hitting this box. And then I've got a single fiber that's going to my ONT, and then I have this other fiber. So in this case, in this hotel, every, I would say, 8 rooms or so is also feeding a remote antenna unit for the cellular system, for the DAS. Okay, so in this case, we've got this inside the room in the closet, and in about every 8 rooms, we've got a fiber connection, a fiber pair, which is coming out. Also, the power is coming out, and it's feeding a remote antenna unit, which is in the hallway right outside of that room. This is connecting to a low-profile DAS antenna as an example. So again, in this box, as things change, as they need new devices, we can add an ONT if we choose to. We can add a remote antenna unit. So today, we talk 4G, but when we look at 5G, now we have smaller cells, we have more bands. So maybe instead of having a remote every 8 rooms, maybe I need it every 4 rooms or every other room or every room, right? Things change, but with this high bandwidth, connection into my room, essentially I can scale. So now 1 cable to come in to feed everything versus, 4 or 8 or 10 copper connectors coming into the room. So that's my kind of the hotel scenario there. This large box here to my your right here is a stadium application. Okay, so this would be something that we've deployed a lot of large football stadiums, basketball arenas, public venues, and so in this case I've got a remote antenna unit which is providing my cellular coverage for my carriers, and I also have a Cisco switch. So this Cisco switch is getting fed off of that aggregation switch that we showed you back in the rack. So again, very flexible system. I want to use a bi-die optic to feed my ONT. In this case, I use a standard duplex SFP to feed my Cisco switch. Okay, but I've got my Cisco switch. This happens to be a 12-port switch. And I also have, in this case, I have some ONTs. So really what I'm showing is kind of 2 scenarios. Scenario 1 would be cellular remote with a Cisco switch as an example. Maybe another customer still wants a cellular remote, but he wants to run it via PON and do a point-to-point connection as an example. But in this box, I need lots of power, right? So you see here, this is a 12-port switch. So if I got 12 ports of PoE plus a remote antenna unit, plus in this case an ONT, I'm exceeding 100 watts really quick. And so this is that connection that's getting fed by my digital electricity connection. And so you'll see I have a single copper connector coming in, or copper pair, which is feeding my digital electricity receiver. And then from this receiver, I'm powering, in this case, my ONT, my remote antenna unit, and my Cisco switch, which is providing PoE. So just another architecture that we support over the SDN platform. Thank you again for your attentiveness. Again, what we're talking about today is the evolution of building technology and how a deep fiber network in combination with a software-defined network can really benefit, we think, a lot of these enterprises and various verticals that we cover. Again, my name is Jason Green, and I'm happy to answer questions.